Imagine you're standing on the absolute highest point of the Shanghai Tower.
Oh, wow. Okay, starting right at the top.
Right at the top. You're hundreds of stories up, and you are leaning over the edge of, well, one of the tallest mega-tall skyscrapers on the entire planet.
Just looking straight down at the pavement.
Exactly, just looking straight down. And I want you to feel that sudden rush in your chest.
Yeah.
You know, that dizzying, stomach-dropping wave of vertigo where your brain is just screaming at you to step back.
Oh, yeah, I hate that feeling. It's like a primal panic.
Right. Well, that massive, terrifying void of empty air, that is the exact distance from the window of your car down to the river gorge when you're driving across the bridge we're looking at today.
It's a scale that almost defies human comprehension. I mean, you are literally suspended in the clouds.
Which is exactly why we are jumping into this deep dive. Our source material today covers the Huajiang Canyon Bridge.
Yeah, which opened up in late September of 2025.
Right, in a really remote Chinese province. And it is honestly a complete redefinition of what human engineering can even do.
It really is.
Okay, let's unpack this. We're going to explore how a single bridge shattered world records, conquered these impossible geographical obstacles that isolated people for centuries, and then inexplicably decided to double as a global hub for extreme sports.
Which is the best part. But to really grasp the audacity of this project, you have to kind of throw away the illusion that your GPS gives you.
What do you mean by illusion?
Well, when you look at a digital map, the world is just this flat, two-dimensional abstraction.
Right, like a video game map.
Exactly. You see point A, you see point B, and your navigation app just draws a neat little straight line right between them.
Yeah, it looks so simple.
It does, but it completely hides the brutal reality of the Earth's surface.
Because you drive out to that straight line, and suddenly the Earth just, well, drops away.
Yeah, you're staring down this jagged, seemingly bottomless gash in the planet.
And historically, if you hit a canyon like that, you either turn around or you spend like days navigating this treacherous dirt path all the way down to the bottom and then painstakingly back up.
Right, but the engineers here chose a slightly different route.
They decided to just float a highway across the sky.
Basically, yeah.
Let's get into the sheer physical dimensions of what they built here in Guizhou province. It crosses the Beipan River, and the bridge itself measures 2,890 meters in total length.
That's almost 3 continuous kilometers of asphalt and steel and concrete just suspended over a void.
It's mind-boggling.
Yeah.
I mean, if you're driving across it at normal highway speeds, you are out over the open gorge for a really significant amount of time.
You're just hanging there.
Yeah. And the main span, the section hanging purely between the two massive support towers, that alone is 1,420 meters.
And just to hold up that specific amount of weight, they had to build support towers that are, honestly, they're essentially skyscrapers themselves.
Right. The north tower is 262 meters tall, and the south tower is 205 meters tall.
And think about the logistics of that for a second. You are building a 262-meter concrete tower, but not in some flat city center with, easy access to cranes and paved supply lines.
No, you're perched on the precarious edge of a mountain cliff.
Exactly. The staging and the material transport alone for a site like that is an engineering marvel.
Just getting the trucks up there.
Right. Every single ton of steel, every cubic meter of concrete, it all has to be hauled up these winding mountain passes before it even becomes part of the bridge.
But the height of those towers, that isn't even the record-breaking part.
No, it's not.
The statistic that absolutely breaks my brain is the clearance below the deck.
The drop.
The drop. The actual road where the cars are driving sits 625 meters above the water level of the river gorge.
Wow.
That is the drop we were visualizing at the start. 625 meters of pure, empty air. So it holds the title for the highest bridge in the world.
And there is this really fascinating, almost paradoxical regional detail buried in the geography here.
Oh, what's that?
Well, by hitting that 625-meter mark, the Huajiang Canyon Bridge claimed the world record, right? Do you know whose record it actually broke?
I think I saw this in the text. It was the Douge Bridge, right? Which crosses the exact same river.
Yes. The Beipan River. It's just 200 kilometers upstream.
That is wild. The same river valley holds the top 2 highest bridges on Earth.
Yeah.
It's like the river has basically carved a trench so hostile and so deep into the earth that engineers are forced to literally surpass their own world records just to get from one side of the province to the other.
It really speaks to the absolute sheer hostility of the terrain out there. I mean, building a megastructure in an environment that unforgiving, it does not happen by accident.
No, and it certainly requires a monumental financial commitment.
Oh, a massive one. Construction on this project began all the way back in January of 2022. They spent years just battling the altitude and the elements.
And then they finally ran load tests in August of 2025.
Right.
Wait, actually, we'll pause on that for a second. I always see the phrase load tests thrown around in these engineering articles, but what does that actually look like for a bridge hanging 625 meters in the air?
Oh, it is easily one of the most tense phases of construction.
I can imagine.
Because before you let the public anywhere near it, you have to prove that all your mathematical models actually hold up in the physical world.
So what do they do?
Well, for a suspension bridge of this scale, they literally drive convoys of fully loaded, heavy commercial dump trucks out onto the deck.
Wait, really?
Yeah, dozens of them just parked end to end. They're mimicking the absolute maximum weight the bridge could ever conceivably hold in, like a catastrophic traffic jam.
That sounds terrifying for the guys driving the dump trucks.
Right. But the engineers then meticulously measure how much the bridge deck sags or, deflects under that immense pressure.
Oh.
They're checking the tension on the cables, the stress on those massive towers, and only when the bridge flexes exactly as predicted and then springs right back into place do they actually sign off on it.
Wow. Well, they obviously passed because it officially opened to traffic on September 28th, 2025.
They did.
And that brings us to the financial reality of all this. The construction cost was 2.1 billion RMB.
Which is roughly a 290 million US dollar equivalent, though in terms of domestic purchasing power and the sheer scale of raw materials that buys in the Chinese infrastructure sector, it is an incredibly massive public works expenditure.
Wait, 2.1 billion RMB for a single bridge.
Yes.
The math just isn't mathing for me here.
How so?
Because the text says this bridge carries the S57 Lujianlong Expressway, right? And it turns a 70-minute drive into a drive that takes just over 1 minute.
Correct.
I am struggling to understand how any government justifies spending that kind of money just to save commuters 69 minutes. I mean, is an hour of saved driving time really worth billions?
If we connect this to the bigger picture, you have to look down at the ground beneath the bridge to really understand the justification.
Okay, what's on the ground?
Well, Guizhou province has historically been a very economically depressed area, and that poverty is directly tied to its geography. The landscape there is defined by karst topography.
Right, the text mentioned that. It's like Guizhou's ground is basically made of Swiss cheese.
That is a very good way to put it, yeah. It's a landscape dominated by limestone that, over millions of years, just dissolves and washes away.
Leaving behind what?
It leaves behind these massive, sudden sinkholes, deep underground cave systems, and these dramatic, really jagged, rocky
That
spires.
sounds gorgeous for a postcard.
Oh, it's beautiful to look at, but it is an absolute nightmare if you're an engineer tasked with laying down a flat, stable stretch of asphalt.
I bet.
And it's a nightmare that acted as a literal fortress wall around the province for centuries.
Wow.
Before this bridge, if you wanted to cross that canyon, you weren't just driving. You were navigating treacherous, winding mountain switchbacks down to the valley floor, loading your vehicles onto slow-moving river ferries, and then climbing painstakingly back up the other side.
That sounds awful.
So those 69 minutes you mentioned, that is not just a frustrating delay on a morning commute.
What is it then?
It is a profound friction point that stifles all economic activity. I mean, think about the logistics. If you're a manufacturing company and it takes your fleet of commercial trucks an extra hour and a half of burning fuel and navigating dangerous mountain passes just to deliver a shipment of basic goods.
Your profit margins just vanish.
Exactly. Or if you're a local farmer in Guizhou trying to get your produce to a wider national market before it spoils, that canyon is essentially a death sentence for your business.
Because industries just refuse to invest in areas where the supply chain is that physically compromised.
Right. So the bridge isn't a shortcut. It is an economic lifeline.
Right, I see. You aren't paying for a shorter drive. You are paying to unlock an entire province's economic potential.
It transforms a formidable geographical barrier into a high-speed, bustling gateway. Suddenly, heavy freight can move seamlessly.
Yeah.
Local businesses are integrated into the broader national economy in a way they literally never could be before. You are dissolving the isolation that causes the poverty.
That is fascinating. But, I mean, if you are betting the economic future of an entire province on a single bridge hanging 625 meters in the sky,
Yeah.
with fleets of commercial trucks rolling across it day and night, you need to be absolutely certain the thing isn't going to snap.
Oh, definitely.
Because it is subject to incredibly high winds up there, massive temperature shifts, expanding and contracting the steel, and just the constant punishing stress of heavy traffic.
You cannot just pour the concrete, string the cables, and hope for the best. At that altitude, safety requires knowing exactly what the structure is experiencing at a microscopic level at all times.
And here's where it gets really interesting. The engineers essentially gave the bridge a nervous system.
They did.
The source text details how they embedded live monitoring directly into the structural DNA of the bridge. They used a fiber optic load cell cable woven right into the carrying cable strands to provide real-time data on the bridge's health.
It's brilliant engineering.
It is, but reading through the specs, I hit a detail that made me highly skeptical.
Oh.
It says this fiber optic cable is embedded in only 3 out of the 217 carrying cable strands.
That's correct, yeah.
Why cheap out on the sensors?
Yeah.
I mean, if you are going through the multi-billion RMB trouble of wiring up a 2,800-meter-long bridge, why not monitor all 217 strands?
It seems counterintuitive, right?
Yeah. How can 3 possibly be enough to know if a megastructure is failing?
Well, it is a very common intuition to assume that more data is always better. Like, why not wire every single inch? But in the physics of structural engineering, particularly with suspension bridges of this magnitude, the goal is actually elegant efficiency.
Okay, unpack that for me.
Think of the main suspension cable like a massive tug-of-war team.
Okay, a tug-of-war team. I'm with you.
If you have a team of 217 people all pulling on a single massive rope together, they are all working in concert, they are all experiencing the exact same macro-environmental stresses,
Right.
the same wind pushing against them, the same weight pulling back. You don't need to walk down the line and ask every single individual person exactly how hard they're pulling to understand the total force.
Oh, I see.
If you attach a highly calibrated strain monitor to just 3 carefully, evenly spaced people on that team, you know the exact tension the entire group is exerting.
Because they are bound together. The behavior of the 3 perfectly mirrors the behavior of the whole.
Precisely. By embedding fiber optic load cells in a strategic representative sample, engineers can extrapolate the live stress of the entire structure with incredible accuracy.
That makes a lot of sense.
And we really should talk about how those fiber optic cables actually work, because it is brilliant.
Please do, because I just picture like a regular internet cable. How does a glass wire tell you if a massive steel bridge is straining?
Okay, so they shoot continuous pulses of light through the microscopic glass fibers embedded in the cable, and glass is incredibly sensitive to physical manipulation.
Right.
When a heavy convoy of trucks drives over the bridge, or a massive gust of wind hits the canyon, the main steel cables stretch and bend microscopically.
Okay.
That physical strain transfers to the embedded fiber optic cable, causing the glass fibers inside to undergo what we call microbending.
So the glass actually warps slightly under the pressure.
Yes. And when the glass warps, it changes the way the pulses of light refract and bounce back to the sensor hub.
Oh, wow.
By measuring those minute changes in the light's reflection, the computer system can instantly calculate the exact physical tension and stress the bridge is experiencing in real time.
That is wild.
Yeah.
It really is a nervous system, like literally pain receptors for a steel giant.
Exactly. And introducing complex, delicate fiber optic sensors into high-tension steel is mechanically very difficult during the spinning process of the main cables.
I can imagine.
Every sensor you add introduces a potential point of friction or, a mechanical weakness. So by limiting it to 3 meticulously chosen strands, they get all the high-fidelity, real-time data they need to ensure structural integrity without overcomplicating or weakening the mechanics of the cables themselves.
Wow. So we have this flawlessly monitored, mathematically perfect structure just floating above the clouds.
Yeah.
It's safe, it's efficient, and it's solving a massive economic bottleneck for Guizhou.
A total game changer for the region.
But they didn't just stop at making it a functional highway. Someone looked at the blueprints for this beautifully engineered crossing over a stunning deep gorge, and they had a wildly creative realization.
Yeah, they did.
They realized the bridge didn't just have to be the transport. It could be a tourist destination all by itself.
What's fascinating here is this is where the project transcends traditional public works infrastructure and becomes something entirely new.
because integrated right into the architectural design of the bridge are these mind-bending tourism facilities. It's not some retrofitted afterthought either. It is built right into the concrete and steel.
It's fully integrated.
Yeah. For example, below the car deck, there is a glass sightseeing walkway.
Oh, just imagine the sensory experience of that.
I'm getting vertigo just thinking about it.
Right. You're walking on a transparent floor. Above your head, heavy commercial trunks are rumbling past, physically vibrating the structure. And beneath your feet, there's nothing but 625 meters of empty air before you hit the rushing waters of the Beipan River.
And it gets so much crazier because the designers look at the immense height of those support towers, the ones perched on the cliff edges, and they capitalized on them.
Oh, yeah.
Beside one of the main towers, they constructed a 207-meter-high, glass-enclosed elevator and staircase.
An elevator ride scaling the side of a mountain gorge inside a transparent box.
A 207-meter vertical drop while you are standing in a glass box.
Incredible.
And, okay, on top of one of those bridge towers, sitting exactly 800 meters above the valley floor, is a specialty coffee house.
That is just...
I just have to laugh at the sheer absurdity and thrill of this concept. Imagine you're on a road trip, right? You pull over at a highway rest stop. You take a massive glass elevator up the side of a bridge tower, and you sit there sipping a vanilla latte 800 meters in the sky.
It's literally monetizing the altitude.
You are eye level with the clouds, while the highway traffic just speeds along hundreds of feet beneath you.
And if the caffeine isn't enough to get your heart rate up, the bridge also includes built-in facilities for bungee jumping and paragliding.
Right. They engineered platforms into the multi-billion RMB expressway specifically so people can voluntarily throw themselves off it.
There is a profound economic brilliance to this dual-purpose design, though.
How do you mean?
Well, the planners looked at the problem of Guizhou's historical isolation, and they approached it from two distinctly different angles simultaneously.
Right.
The primary goal is fulfilled, obviously. The highway brings commercial shipping, it solves the logistics nightmare, and it provides traditional economic integration for the local industries.
Right.
But they recognize that the very thing that kept people out, that dramatic, terrifying karst topography, is the exact scenery that will draw people in.
They turned their biggest geographical liability into their biggest asset.
Precisely. By turning the infrastructure itself into an engine for extreme tourism, they are creating a completely new revenue stream for the province.
That's so smart.
Extreme sports enthusiasts, international sightseers, architecture nerds, and, people who just want a really crazy cup of coffee. They will travel from all over the world to experience the sheer scale of the Huajiang Canyon Bridge.
Yeah, they absolutely will.
It is a masterclass in maximizing the return on a public works investment. You aren't just facilitating trade, you are creating an entirely new industry on top of a bridge tower.
It is the ultimate two-for-one deal. So what does this all mean? When we step back and look at the whole picture here, we're looking at a true marvel of the modern world that forces us to basically rethink what infrastructure can be.
Absolutely.
We have the 2.1 billion RMB investment that conquered impossible jagged limestone mountains, took a grueling, day-ruining 70-minute trek through a dangerous canyon and turned it into a 1-minute flight across the sky. It provided a vital economic lifeline to a historically isolated province, plugging them right into the national supply chain. And because human beings are delightfully crazy, it doubles as an extreme sports hub with a nervous system made of light, where you can drink coffee above the clouds and bungee jump off a world record-holding structure.
This raises an important question. As our global infrastructure projects become increasingly monumental, and as they integrate more seamlessly and dramatically with the natural landscape, it challenges our fundamental assumptions about travel.
How so?
We have always viewed roads, tunnels, and bridges simply as the mechanisms we use to get to our destinations.
Right, there was just the journey.
But if a functional suspension bridge hanging over a gorge can simultaneously operate as an extreme tourism hub, when does the commute stop being the journey and start becoming the vacation itself?
Wow.
Imagine what other everyday pieces of infrastructure, our train stations, our water dams, our highway interchanges might evolve into as engineering continues to blur the line between utility and destination.
I love that thought. The obstacle in the middle of the map might just become the best part of the trip. Well, thank you for joining us on this deep dive into the Huajiang Canyon Bridge. Keep your curiosity alive. Keep looking for the stories hiding behind the concrete and steel, and we will catch you on the next one.
el mundo tridimensional de la experiencia ordinaria, o sea, el universo lleno de galaxias, estrellas, planetas, casas, rocas y personas, es un holograma, una imagen de la realidad codificada en una superficie bidimensional distante.
Qué barbaridad de cita, ¿verdad? Y, a ver, lo fuerte es que en la física teórica esta declaración de Leonard Susskind no se trata como, no sé, como una metáfora literaria ni un ejercicio de filosofía barata.
Para nada.
Es una conclusión matemática pura y dura a la que han llegado después de décadas lidiando con las ecuaciones más fundamentales del cosmos.
Es que fíjate, yo lo pienso y me explota la cabeza. Para quienes nos escuchan, imaginemos por un momento que toda esta tridimensionalidad que damos por sentada, la profundidad, el volumen real que sentimos al caminar por una habitación o al mirar al cielo.
Sí, sí, esa sensación de espacio.
Exacto. Imagina que todo eso fuera en realidad como un entorno inmersivo generado por código, como si creyéramos que estamos jugando dentro de un entorno de realidad virtual infinito, pero en realidad todo lo que somos y tocamos está escrito en el disco duro plano de la consola.
Es una analogía brutal. Sí.
Pues hoy, en esta inmersión profunda, nuestra misión es precisamente desentrañar esta locura, el principio holográfico. Tenemos unas fuentes maravillosas hoy, centradas en un artículo documental exhaustivo que repasa desde los primeros trabajos sobre termodinámica de agujeros negros hasta los últimos avances sobre holografía celestial.
Que es lo más puntero que hay ahora mismo.
Así es. Y el objetivo de nuestro análisis es traducir estos conceptos tan densos de la gravedad cuántica y la teoría de cuerdas para entender por qué la ciencia moderna sospecha que el universo podría ser una proyección.
Y bueno, para entender cómo se desmorona el concepto mismo de volumen, tenemos que ir al único lugar del universo donde nuestras matemáticas de toda la vida se rompen por completo.
Los agujeros negros, claro.
Exacto. Y todo este lío empieza con algo tan aparentemente básico como la entropía. A ver, en los años 70, Jacob Bekenstein se dio cuenta de algo crucial para mantener intacta la segunda ley de la termodinámica.
Esa ley que dice que el desorden del universo siempre va a más, ¿no?
Eso es. Pues Bekenstein dedujo que si tiras materia, digamos gas caliente que tiene mucha entropía, dentro de un agujero negro, esa entropía no puede simplemente desaparecer de la existencia.
Porque si desaparece, la entropía total del universo disminuiría.
Y eso es físicamente imposible, violaría las leyes de la termodinámica. Así que el agujero negro debe tener una entropía propia que aumente cuando se traga ese gas.
Me cuadra.
Pues aquí viene el descubrimiento rompedor. Bekenstein y un poco después Stephen Hawking demostraron matemáticamente que la cantidad de entropía de un agujero negro no es proporcional a su volumen tridimensional.
O sea, no escala con el radio al cubo como pasaría con cualquier objeto normal.
Nada de eso. Es estrictamente proporcional al área de su horizonte de sucesos, es decir, al radio al cuadrado. De hecho, Hawking calculó que es exactamente un cuarto de esa área medida en pequeñísimas unidades de Planck.
A ver, frena un momento ahí, porque quiero asegurarme de que pillo esto. Si yo lleno una caja con bloques de madera, caben tantos bloques como volumen tenga la caja, ¿vale?
Claro, la geometría clásica de toda la vida.
Pues Bekenstein y Hawking nos están diciendo que en un agujero negro la cantidad de información o de caos térmico que cabe depende solo del papel de regado que lo envuelve, no del tamaño de la caja en sí.
Es una forma fantástica de visualizarlo, ¿sí?
Pero ¿cómo es físicamente posible que el interior no importe en absoluto? Suena a magia, no a física.
Parece contraintuitivo a tope, lo sé. Pero, a ver, piensa en la relatividad general. Tenemos que mirar el horizonte de sucesos desde la perspectiva de alguien que observa desde lejos, no desde la perspectiva de la pobre silla o la nube de gas que está cayendo dentro.
Vale, me pongo en la piel del observador lejano.
Debido a la gravedad inmensa del agujero, hay una dilatación temporal extrema. Para ti, que miras desde fuera, el tiempo literalmente se va frenando hasta detenerse casi por completo justo en ese borde, en el horizonte de sucesos.
¡Ostras, claro!
Entonces, desde tu marco de referencia, los estados cuánticos de la materia que cae nunca parecen cruzar la frontera para entrar al volumen. Se congelan, se aplanan y se quedan, pues eso, impresos en esa superficie bidimensional.
O sea, la información se queda como untada en la envoltura.
Exactamente. La cantidad de información que puede tragarse ese agujero está dictada por los píxeles de esa superficie, por así decirlo. Y claro, para un holografista estricto, el interior del agujero pierde relevancia.
Ya, Pero entiendo que no toda la comunidad científica compra esto a ciegas, ¿no? En nuestras fuentes se menciona que esto sigue generando bastante fricción teórica.
Muchísima. A ver, para ser rigurosos hay que hablar del panorama completo. Existen soluciones matemáticas clásicas a las ecuaciones de Einstein que permiten configuraciones súper extrañas, unas topologías que se conocen como las bolsas de oro de Wheeler.
Bolsas de oro. Me encanta el nombre, pero ¿qué son exactamente?
Pues imagina un espacio que tiene un cuello de botella en la entrada muy estrecho, una garganta minúscula, pero que luego se abre a un universo interior gigantesco.
Vale, como una de esas carpas de circo que por dentro son enormes.
Eso es. En este caso, el área de la entrada, el horizonte, es ridículamente pequeña. Así que según la ley de Bekenstein y Hawking, su límite de entropía debería ser bajísimo.
Claro, porque hay poco papel de regalo.
Exacto. Pero el volumen interior es tan inmenso que según la física clásica, podría contener una cantidad casi infinita de cosas, mucha más entropía de la que permite su superficie.
¡Ostras! Entonces estas bolsas de oro ponen en jaque toda la idea de la holografía en los agujeros negros.
Sí, plantean un desafío directo a la ley del área. Y por eso es un debate que sigue súper vivo hoy en día. Pero bueno, si aceptamos al menos por ahora que la superficie dicta el contenido en la mayoría de colapsos gravitacionales,
Estamos cambiando silenciosamente las reglas del juego sobre de qué está hecho el universo, ¿verdad?
totalmente. Porque si el área es lo que mide el contenido, ya no estamos hablando de rocas, o de gas, o de átomos chocando. Estamos hablando de información.
Y aquí es donde entra la famosa frase de John Archibald Wheeler, que acuñó eso de "it from bit". La idea de que el mundo físico es, en el fondo, información, y que la materia y la energía son solo, incidentes, efectos secundarios.
Es que es un cambio de paradigma brutal. Wheeler se preguntaba, y esto lo citaba Bekenstein en un artículo mítico de Scientific American, si podíamos realmente ver un mundo en un grano de arena, como decía el poeta William Blake, o si era solo una licencia poética.
Pues parece que no era solo poesía.
Para nada. Pero para sostener que el mundo físico está hecho de información, tienes que demostrar que las leyes de la termodinámica y las de la informática hablan el mismo idioma.
Y eso fue exactamente lo que pasó, de una forma súper inesperada además, porque a finales del siglo XIX tenemos a Ludwig Boltzmann definiendo la entropía de un sistema físico, ¿no? Contando de cuántas formas puedes organizar las partículas de un gas en una habitación.
Sí, física pura y dura, casi de la era del vapor.
Y luego, un siglo después, en 1948, aparece Claude Shannon, que no tenía nada que ver con los gases. Él trabajaba en telecomunicaciones, definiendo la entropía de la información para ver cuánto podía comprimir los datos en un canal.
Exacto. Y lo alucinante es que las matemáticas de Shannon resultaron tener exactamente la misma estructura logarítmica que las ecuaciones de Boltzmann.
O sea, yo esto lo leí en las fuentes y me quedé fascinada. Básicamente, la física y la informática están hablando el mismo idioma sin saberlo. Es decir, calentar el agua de una olla y comprimir un archivo zip en un ordenador siguen exactamente las mismas leyes matemáticas fundamentales del universo.
Es que es brutal. El número de disposiciones moleculares que contaba Boltzmann refleja la cantidad exacta de bits de información de Shannon que necesitarías para programar esa misma materia. La única diferencia entre las dos fórmulas son las unidades de medida.
O sea, que puedes tratar cualquier espacio del universo no como un tupper lleno de partículas, sino como un disco duro, como una memoria USB.
Tal cual. Ambas entropías son conceptualmente equivalentes. Pero ojo, que esta misma revelación maravillosa fue la que desató la mayor guerra intelectual en la física teórica reciente.
Uy, sí, la crisis que montó Stephen Hawking.
Madre mía, ¿la que lió? A ver, Hawking se dio cuenta de algo sobre los agujeros negros. Si tienen entropía y temperatura, obligatoriamente tienen que emitir radiación.
La famosa radiación de Hawking.
Eso es. Él calculó que esta luz saliente hace que el agujero negro pierda masa muy lentamente y eventualmente, tras miles de millones de años, se evapore por completo.
Vale, el agujero desaparece. Pero, ¿por qué eso rompió los esquemas de toda la comunidad?
Por la naturaleza de esa radiación. Hawking argumentó matemáticamente que esa radiación térmica es completamente aleatoria, que no guarda absolutamente ninguna relación con la materia que cayó dentro en primer lugar.
A ver si lo entiendo. Si yo lanzo una enciclopedia enorme a un agujero negro,
El agujero se la traga.
y Hawking decía que el conocimiento de ese libro se borraba para siempre, porque lo único que salía de ahí era calor aleatorio.
Exacto. Si el estado final es solo ruido térmico puro y el agujero desaparece, la información de la enciclopedia se ha destruido. Ha dejado de existir en el universo.
Y eso es un problema gravísimo para la mecánica cuántica, ¿no? Por el tema de la unitariedad.
Un problema gigantesco. La unitariedad cuántica exige que la información nunca se destruya, que los estados cuánticos no se conviertan de repente en mezclas probabilísticas aleatorias. El presente tiene que contener suficiente información para, en teoría, poder rebobinar las leyes de la física y ver exactamente el pasado.
¿Y si solo sale calor aleatorio? No puedes rebobinar para recuperar el texto de la enciclopedia. La física cuántica colapsa.
Pues ahí es donde entra al rescate Leonard Susskind, con su interpretación holográfica. Él se negó a aceptar que la información se perdiera y argumentó que las fluctuaciones u oscilaciones del horizonte de sucesos contienen una descripción completa tanto de la materia que entra como de la que sale.
Mal. Susskind dice que no, espera. El texto de esa enciclopedia sigue escrito en las vibraciones de la superficie bidimensional del agujero negro. Pero ¿cómo demuestras algo así? ¿Cómo es que ese agujero negro es como un proyector de cine extremadamente complejo?
Pues aquí es donde entra la teoría de cuerdas. Susskind, que de hecho es uno de los padres fundadores de esta teoría, identificó estados de cuerdas altamente excitados con los agujeros negros ordinarios.
Espera, ¿cómo es eso de un estado altamente excitado?
A ver, en teoría de cuerdas, las partículas no son puntitos, son pequeñas cuerdas unidimensionales que vibran. Si inyectas muchísima energía, una cuerda se alarga y se enreda sobre sí misma de forma súper caótica. Forma una especie de bola de cuerdas.
Vale, me lo imagino como un ovillo de lana gigante y enredado.
Eso es. Pues Susskind demostró que cualquier agujero negro ordinario sirve como base para describir la teoría de cuerdas de manera holográfica, el espacio-tiempo emergiendo de un horizonte de menor dimensión. Las vibraciones de esa maraña en el horizonte codifican absolutamente todo lo que cayó.
Entonces la enciclopedia nunca se perdió. Siempre estuvo ahí, bailando en la superficie. Y la radiación de Hawking acaba llevándose esa información sutilmente codificada hacia el exterior. ¡Qué barbaridad!
Es una maravilla. Pero claro, todo este debate de Susskind era genial conceptualmente, pero necesitaba una demostración matemática súper rigurosa para que no se quedara en pura filosofía cuántica, ¿sabes?
Y esa prueba irrefutable llegó en 1997. El triunfo matemático que transformó la física para siempre, cortesía del físico argentino Juan Maldacena. La correspondencia ADS-CFT.
La dualidad de Maldacena, probablemente el hito más grande de la física de altas energías de las últimas décadas.
Vamos a desgranar esto porque en las fuentes queda clarísimo que es vital. ¿Qué es exactamente lo que conecta esta dualidad? Empecemos por el lado ADS.
Vale. Por un lado, Maldacena usa espacios anti-de Sitter, que es lo que significa ADS. Es un modelo matemático de espacio-tiempo que tiene gravedad cuántica y teoría de cuerdas en su interior. Es como un universo encerrado en una botella matemática.
Ya, pero es un espacio muy particular, ¿no? No es el espacio en el que vivimos nosotros.
No, no lo es. Es un espacio hiperbólico con curvatura negativa. Para que nos hagamos una idea visual, los físicos usan mucho la imagen de los grabados circulares de Escher, esos donde los murciélagos o los ángeles se van haciendo infinitamente pequeños a medida que se acercan al borde exterior.
Vale, lo tengo en la cabeza. Entonces, dentro de ese círculo de Escher, tenemos gravedad y volumen. ¿Y qué hay en el borde, en la frontera de ese modelo?
Ahí es donde está la CFT, la teoría de campo conforme. Es una teoría cuántica que describe partículas elementales interactuando, pero ojo, en un espacio plano y con una dimensión menos. Y lo más importante, sin gravedad. Cero gravedad en la frontera.
Vale. Entonces, Maldacena propone que lo que pasa dentro del círculo con gravedad en 3 dimensiones
Sí.
es matemáticamente el mismo fenómeno exacto que lo que pasa en el borde plano de 2 dimensiones sin gravedad.
Exacto. Proporciona la realización más exitosa del principio holográfico. Demostró que son 2 diccionarios distintos para describir la misma realidad exacta.
Ostras, en las fuentes lo mencionan como una dualidad fuerte-débil. Yo creo que para entender el impacto que tuvo esto, se puede pensar con una analogía ingenieril, ¿no?
A ver, cuenta.
Es como tener un problema de ingeniería en la frontera que es imposible de resolver, porque las matemáticas cuánticas son intratables, como si estuviera escrito en un español complicadísimo. Así que usas la dualidad para traducirlo al interior del volumen, al japonés.
Sí.
Y resulta que en japonés, o sea, en el lado de la gravedad, la interacción es súper débil y se convierte en matemática básica. muy fácil de calcular. Y cuando tienes el resultado, simplemente traduces la solución de vuelta a la frontera. Es un atajo matemático increíble.
Es un atajo majestuoso. Por eso el artículo de Maldacena es el más citado en la historia de la física de altas energías. Superó las 10.000 citas en 2015 y a día de hoy los físicos de la materia condensada o de física nuclear lo usan en laboratorios reales para calcular cosas.
Claro, les facilita la vida una barbaridad. Pero oye, esto nos lleva a un territorio aún más alucinante, si cabe. Si las matemáticas de Maldacena funcionan tan bien, y Bekenstein tenía razón con que el universo tiene un límite de información definido por áreas,
Sí.
surge una pregunta obligada. ¿Significa esto que el universo físico, el espacio en sí mismo, tiene una resolución máxima, como la pantalla de un televisor?
Pues, por pura necesidad lógica, sí. El límite de Bekenstein sugiere que para una energía y un volumen dados hay un tope máximo de información que puedes meter. Si superas ese tope, colapsa en un agujero negro.
Vale.
Esto implica que la materia y el espacio no pueden subdividirse infinitamente, porque si el espacio fuera analógico y continuo hasta el infinito, cabría información infinita violando la regla empírica.
Claro, o sea que tienen que existir partículas fundamentales de nivel último, los píxeles de la realidad.
Exacto, una escala mínima a nivel de Planck, por debajo de la cual el universo ya no tiene más resolución.
Madre mía, ¿y alguien ha intentado medir estos píxeles empíricamente? Porque la teoría es preciosa, pero necesitamos laboratorios.
Claro, y ha habido intentos muy sonados. Por ejemplo, Craig Hogan, un investigador del Fermilab, propuso una idea muy audaz. Dijo que, si somos un holograma proyectado, el límite de información debería crear una especie de ruido holográfico de fondo.
Como el ruido estático de una tele vieja si te acercas mucho.
Eso es. Y Hogan creía que los detectores de ondas gravitacionales, concretamente el interferómetro GEO 600 en Alemania, serían lo bastante sensibles como para captar este temblor continuo en el espacio-tiempo.
¡Ostras! ¿Y lo captaron?
Pues, lamentablemente para Hogan, no. Y de hecho la refutación final vino del espacio. En 2011, la Agencia Espacial Europea, usando el Observatorio Espacial Integral,
Sí, recuerdo leer sobre esto en el documento.
pues analizaron la luz de brotes de rayos gamma lejanos, buscando simetrías minúsculas, y demostraron que ese supuesto ruido holográfico estaba completamente ausente, al menos hasta una escala de 10 elevado a menos 48 metros.
O sea, una precisión abrumadora que contradecía de lleno la predicción de Hogan.
Por completo.
Pero, a ver, yo me pregunto, saber que la materia no puede dividirse infinitamente significa que el universo está pixelado de base. ¿El hecho de que Integral no encontrara el ruido de Hogan debería desanimarnos o simplemente significa que los píxeles de nuestra realidad son muchísimo más pequeños y nítidos de lo que creíamos?
Es exactamente lo segundo. La comunidad no descartó el principio holográfico por esto, solo descartó el modelo específico que propuso Hogan para medirlo a esa escala en concreto.
Ya, claro, era un modelo un poco optimista.
Demasiado optimista, sí. Pero el impulso por probar la holografía en el mundo real sigue imparable. Y la prueba definitiva es lo que se conoce hoy como holografía celestial.
Ah, claro, el gran proyecto de la física actual. Cuéntanos sobre esto, porque sé que es un esfuerzo monumental, liderado por gente como Andrew Strominger y Sabrina Pastersky.
Pues mira, el mayor problema que teníamos con Maldacena es que funcionaba en espacios matemáticos cerrados, esos anti-de Sitter que comentábamos con curvatura negativa.
Pero nuestro universo real, astronómicamente hablando, es un espacio asintóticamente plano.
Exactamente. Así que el equipo de Strominger y Pastersky está intentando aplicar la holografía directamente a espacios planos como el nuestro. La idea es proyectar la información cuántica del interior en una especie de esfera celestial bidimensional que estaría situada en el infinito.
Como una gigantesca cúpula matemática envolviendo todo el universo observable.
Sí, eso es. Y lo emocionante es que creen que esto tiene firmas detectables reales. Esperan probar estas simetrías holográficas observando la radiación que emiten las colisiones de agujeros negros, utilizando detectores avanzados de ondas gravitacionales como el LIGO o el futuro LISA en el espacio.
Es brutal. Si lo consiguen, confirmarían que las reglas del juego de nuestro cosmos entero están escritas en los límites del universo.
Ni más ni menos.
Bueno, si hacemos un resumen conectivo de este viaje alucinante, porque menuda locura de sesión, empezamos en la superficie inescrutable de un agujero negro, donde el límite de Bekenstein nos dijo que la superficie importa más que el volumen.
Y eso nos llevó a descubrir que la termodinámica clásica de Boltzmann y la teoría de la información de Shannon son exactamente equivalentes.
Descubrimos cómo la teoría de cuerdas de Susskind resolvió esa terrorífica paradoja de la información de Hawking. Luego comprobamos la inmensa elegancia matemática de la dualidad de Maldacena.
Sí,
Y finalmente hemos terminado buscando los mismísimos píxeles de nuestra existencia a través de los detectores de ruido y la holografía celestial.
un recorrido súper completo, sin duda.
Y yo quiero dejar una última reflexión para conectar todo esto a nivel personal. Porque para quienes nos escuchan, la próxima vez que miren a su alrededor, ya sea cogiendo una taza de café, mirándose las manos o simplemente observando las estrellas esta noche,
Es una locura pensarlo, sí.
es fascinante pensar que absolutamente toda la tridimensionalidad que experimentamos, el volumen, el espacio que nos separa de las cosas, podría ser el holograma increíblemente rico de un código escrito en los bordes del cosmos.
Cambia por completo tu forma de percibir el día a día.
Totalmente. Pero todo esto me deja con una última incógnita, algo para darle vueltas mucho después de que termine esta inmersión profunda. A ver qué te parece.
Dispara.
Si resulta que toda nuestra compleja realidad tridimensional, nuestro olor, nuestra alegría, la historia entera de la Tierra es simplemente la proyección desde una superficie de 2 dimensiones lejana,
Sí.
¿quién o qué está iluminando esa superficie para proyectar el holograma que nosotros llamamos vida?
Pues, madre mía, menuda pregunta para terminar.
Ahí lo dejo. Muchas gracias por acompañarnos en este viaje. Nos despedimos por hoy. Hasta la próxima inversión profunda.
Usually when we think about Paris, there's this expectation of, like, glittering excess, right? The city of light.
Oh, absolutely.
You picture the grand boulevards, the cafes, just the sheer abundance of culture and food. It's this beacon of civilization. And it feels entirely permanent, like you really can't imagine it any other way.
Yeah, I mean, it's a city that was built on a scale that projects invincibility. It's, a center of gravity for the entire European continent. It was carefully designed to reflect power, wealth, and just this endless flow of resources.
Right. But then you look at what happened in the winter of 1870, and suddenly that invincibility just vanishes.
That completely evaporates, yeah.
We're looking at a scenario where the most glamorous city on Earth is just completely cut off from the outside world, surrounded,
Right.
freezing, and fundamentally starving.
It is the absolute definition of a societal pressure cooker, a complete reversal of reality almost overnight. I mean, the very infrastructure of luxury becomes completely useless in the face of just brutal medieval warfare.
Welcome to this deep dive. Today, we are taking you right into the heart of the Siege of Paris, which lasted from September 1870 to January 1871.
A really intense 4 months.
Truly, we're pulling from a comprehensive Wikipedia overview of the siege to explore our mission for today. We want to see how the glittering center of 19th century Europe was trapped, how the people inside were forced to adapt in just truly unimaginable ways, and how this 4-month nightmare permanently altered world history.
It really did change everything.
Okay, let's unpack this. Because to understand the sheer desperation of the siege, we first have to understand the immense scale of the trap that was laid for the French.
Right, so to set the stage for you, it's late 1870. The Franco-Prussian War is just raging. And the Second French Empire, which had been, trying to reassert its dominance over continental Europe, had just suffered a completely catastrophic collapse.
Yeah, the Battle of Sedan, right?
Exactly. On September 2nd, the French suffer this devastating defeat. And their emperor, Napoleon III, is actually captured on the battlefield.
Which is just wild to picture. The sitting emperor is taken prisoner.
Right.
That creates this immediate, massive power vacuum in Paris. So the empire falls. The Third French Republic is hurriedly declared under this provisional government of national defense. And meanwhile, you have 2 massive Prussian armies marching right toward the capital.
Basically unopposed.
Yeah. King William I of Prussia and his chief of staff, Helmuth von Moltke, are personally leading this advance.
And inside Paris, the newly appointed commander-in-chief, General Louis-Louis Trochu, is just frantically trying to mount a defense before the iron ring closes around them.
And the scale of this defense is wild to picture. I mean, Trochu manages to assemble around 513,000 potential defenders.
Which is a huge number.
It sounds like an unstoppable force on paper, 500,000 men. But you look at the composition of that number, and the reality is, well, it's much bleaker.
Oh, absolutely. Because half of those men are compulsorily enrolled National Guardsmen.
Right.
They have absolutely no training, no discipline, and they are about to face a battle-hardened Prussian war machine.
Exactly. A paper army cannot hold off disciplined artillery.
But what they lacked in, like, professional soldiers, they really tried to make up for in physical fortifications.
They went all out.
They did. Paris was already surrounded by a 33-kilometer wall, the Thiers Wall, and a ring of 16 detached forts. And the provisional government put something like 12,000 workers to task digging earthworks day and night.
They even sealed off the Paris catacombs, didn't they?
Yeah, the catacombs and the surrounding limestone quarries, they sealed them so the Prussians couldn't tunnel their way in.
That is so intense. They tore up roads, they blocked the railroad entrances. I read they cleared entire forests and leveled suburban houses outside the walls just to deny the Prussians any cover.
Right, and to improve their own artillery sightlines.
Exactly. They even placed electrically triggered mines on certain approaches to the city. Like, they were treating the city itself as a giant fortress.
What's fascinating here is the internal debate within the Prussian High Command as they approached these massive defenses.
Oh, right, they weren't all on the same page.
Not at all. On one side, you have the military strategist, General Moltke. He looked at those defenses, and he never actually intended to attack the city walls directly.
Too risky.
Yeah. His strategy was a methodical siege. He wanted to surround Paris, cut all the supply lines, and just slowly snarve the city into submission.
I mean, he figures, why waste Prussian lives charging a fortified wall when hunger will just do the job for free?
Exactly. Plus, he knew an all-out bombardment on a civilian center is going to create a massive PR disaster.
Right, the international optics.
He was highly aware of that. Bombarding Paris would violate the accepted rules of engagement of the era. It could easily turn neutral countries against the Germans.
But on the other side of the war room, you have Chancellor Otto von Bismarck.
Yeah.
And he is playing a much larger geopolitical game.
Yeah, Bismarck doesn't care about a methodical, patient starvation.
No, he is looking at the political clock ticking down.
He is terrified that a prolonged siege will bankrupt the German economy, and that it would spread disease among the troops as winter sets in.
Because it's getting cold.
Right. But more importantly, he fears that if this drags out, neutral powers like Britain or Russia might decide to intervene to restore the balance of power in Europe.
Oh, wow.
Or that the French provinces might have time to raise a new massive army to attack the Prussians from behind. So Bismarck wants a brutal bombardment to force a quick surrender.
But for the first several months, Moltke's strategy of patience actually wins out. The Prussians encircle the city completely by September 19th, and they just wait.
They literally just sit there.
It's like bracing for a Category 5 hurricane by boarding up all your windows, locking the doors, hoarding supplies, except the hurricane decides not to blow your house down.
Right.
Instead, this massive Prussian army just pitches a tent on your front lawn for 4 months, crosses its arms, and waits to see who runs out of food first.
It is a textbook battle of attrition. The Prussian strategy relied on a simple mathematical certainty. A city of roughly 2 million people consumes an astronomical amount of calories.
And the Parisian authorities really thought they could outlast the math.
They really did.
They had stockpiled cereals, salted meat, preserves. They stored massive amounts of grain inside the Grand Opera Garnier.
Which is such a surreal image.
It is. And they packed the famous Bois de Boulogne Park with livestock. We're talking 250,000 sheep and 40,000 oxen just grazing in the city parks.
The government calculated they had enough wheat and flour to last for 80 days.
Okay, 80 days.
Because they assume, like many do at the start of a conflict, that this would be a brief affair, that a relief army would break the siege long before the flour ran out.
But by mid-November, the reality of the blockade sets in. The fresh meat is entirely gone.
Completely gone.
And the descent of the Parisian diet is shockingly fast. Once the livestock vanishes, they turn to horses.
Yeah, and this wasn't just like a fringe survival tactic. Horse meat became the primary protein for the entire city for a while.
But a finite number of horses meant that eventually the butchers had to look elsewhere. Soon, dog and cat meat appeared in the shop windows.
The psychological shift required for a society to start eating its pets is profound. It really strips away the veneer of civilization and replaces it with pure survival instinct.
And it gets much darker. The sources note they eventually turned to rats.
Yes.
Though surprisingly, consumption of rats was relatively low.
Right. People were terrified of disease.
And ironically, it was quite expensive to prepare rat meat in a way that made it edible.
Yeah, it required heavy sauces, spices, and elaborate preparation just to mask the reality of what they were consuming.
The chefs of Paris were attempting to apply high-end culinary technique to vermin.
It was a desperate attempt to domesticate the utter desperation of starvation.
The contemporary menus from the Latin Quarter in our sources are mind-blowing.
They really are.
They list items like dog liver skewers a la maître d'hôtel,
Wow.
minced saddle of cat with mayonnaise,
Yeah.
and rat salami. They even offered a plum pudding with rum and horse marrow.
I mean, you do what you have to do.
Right. But the pinnacle of this tragedy, the detail that really illustrates the desperation,
Yeah.
is the fate of the zoo animals at the Jardin des Plantes.
Once the stray cats and dogs were depleted, the city looked to the exotic animals.
Yeah.
Antelopes, camels, and yaks were slaughtered. Even castor and pollux, the city's beloved only pair of elephants, were eventually shot for their meat.
There was literally an elephant consommé on a Christmas menu. The irony of eating elephant soup while freezing in your own home is just staggering.
Because the hunger was compounded by a brutal environmental reality. The winter of 1870 was exceptionally harsh. Temperatures plummeted to 7 degrees Fahrenheit.
Which is, what, minus 14 Celsius?
Exactly.
That level of cold is dangerous under normal circumstances.
Right.
But coal gas was strictly rationed because the government needed it to inflate hot air balloons.
Right.
Oil was requisitioned, so people had to rely on wood, and a city of 2 million burns through firewood incredibly quickly.
The citizens of working-class neighborhoods were so desperate for fuel that they chopped down their local street trees.
Oh, wow.
And when those were gone, they moved into the wealthy western districts and started cutting down the beautiful, iconic trees along the Champs-Élysées and Avenue Foch, just stripping the city bare just to survive the freezing nights.
And with cold and hunger comes disease, smallpox, pneumonia, and a massive spike in typhoid.
Yeah, because the siege cut off access to clean water, Parisians were forced to drink directly from the River Seine.
Which was basically an open sewer at that point.
Exactly. By January, between 3,000 and 4,000 people were dying every single week.
Here's where it gets really interesting, because when you hear numbers like that, it sounds like an apocalypse that spared absolutely no one. But did everyone suffer equally?
No. The suffering was intensely stratified by class. Many of the wealthier residents were quite well positioned to weather the siege.
How so?
Well, before the encirclement was even complete, those with capital bought up massive stores of preserved foods and hoarded fuel.
So the wealthy are eating preserved delicacies in warm rooms. What's the mechanism that leaves the working class eating rats in the cold?
It was the complete failure of the government's economic interventions. Early attempts at price controls failed completely because there was no enforcement mechanism.
So no one actually followed the rules.
Right. And this allowed a massive black market to thrive. If you were poor, the government price loan didn't matter because the food simply wasn't available at that price. It was all being sold under the table to the highest bidder.
The only lifeline for many poor families was the miserable 1.50 francs a day that the men earned serving in the National Guard.
And that burden fell overwhelmingly on poor women and children. Infant mortality soared because there was absolutely no fresh milk.
Right.
Anyone who had an occupation, even just a guardsman, warming himself in a bistro while his wife queued for hours in the freezing cold for bread scraps, had a statistically better chance of survival.
This intense inequality and psychological strain didn't just cause despair, though. It boiled over into a desperate need for action. The citizens of Paris weren't going to just sit quietly and freeze.
No, the political pressure on General Trochu became so intense that his hand was basically forced.
He had to do something.
He had to launch offensives, if only to break the psychological tension inside the city. General Trochu authorized several massive military sorties attacks pushing out from the city at places like Le Bourget, Villiers, and Buzenval.
Tens of thousands of men pushing out into the freezing winter. But why couldn't 500,000 defenders punch a hole through the Prussian lines?
Because warfare had fundamentally changed, and the French were totally unprepared for it. The Prussian artillery doctrine was vastly superior.
Okay.
The Prussians had spent months digging well-concealed, deeply entrenched positions. During a breakout attempt at Le Bourget in late December, the French soldiers pushed forward, failed to break the line, and were forced to camp overnight in the trenches.
Oh, no.
With no fuel for fires and 7-degree Fahrenheit weather, there were over 900 cases of frostbite from that single night. The attacks resulted in thousands of casualties and essentially zero strategic gain.
So the physical walls of the siege were impenetrable, so they decided to go over them. The airmail. Since the Prussians had cut the physical telegraph cables, including a secret one hidden in the bed of the Seine, and ground couriers were easily intercepted, the sky was really the only way out.
A photographer and balloonist named Felix Nadar, along with Eugene Godard, recognized the necessity and set up balloon manufacturing workshops.
And where did they put them? Inside empty dance halls and train stations.
Right. The Gare du Nord and the Gare de Lyon were transformed from transit hubs into aerospace factories.
The scale of this operation is deeply impressive. They launched 66 balloon flights during the siege.
That's a lot of balloons.
These flights carried roughly 2.5 million letters out of the besieged city. They even smuggled out their own Minister of War, Léon Gambetta, in a balloon so he could try to rally new armies in the French provinces.
Yeah.
And because a hot air balloon has no steering wheel, you are completely at the mercy of the wind. One balloon accidentally set a world distance record by blowing all the way to Norway.
Which is incredible.
Yeah.
But the limitation, of course, was that the prevailing winds only allowed balloons to fly out of Paris.
Right.
They couldn't fly back in against the wind to deliver news or instructions. They needed a two-way system.
And the solution was the homing pigeon.
Exactly.
They would pack these pigeons into the outgoing balloons, fly them over the Prussian lines, and then release them in the provinces to fly back home to Paris.
It's brilliant.
But you run into a massive data problem. A pigeon can't carry a heavy mailbag of handwritten letters.
No, the technological innovation required to solve this is staggering. Initially, they tried writing tiny messages, but a photographer named René Dagron revolutionized the process with microphotography.
How did he do it?
He would take hundreds of printed messages, arrange them on a large board, and photograph them. He then reduced that image onto a tiny film emulsion, stripped the film from the glass plate, and rolled it tightly into a small quill.
It's like a 19th century zip file. You compress all this data into a microscopic physical format, attach that quill to a biological drone, the pigeon's tail feather, and send it over enemy lines.
That's a great way to put it.
And when the pigeon arrived in Paris, they would project the microfilm onto a wall using a magic lantern. And clerks would transcribe the messages. One pigeon could carry thousands of messages.
Yes, and despite the Prussians bringing in falcons to hunt the pigeons and the winter weather freezing many of the birds, they still managed to deliver over 60,000 messages back into Paris.
That level of ingenuity and resilience deeply frustrated Chancellor Bismarck. The French were starving, freezing, and yet they were still communicating with the outside world.
Yeah, as the winter dragged on into January, Bismarck's fears about international intervention really peaked. He finally overruled General Moltke's strategy of patient starvation.
He had enough.
Bismarck got the green light to use his heavy Krupp siege guns.
The bombardment begins on January 5th, and they aren't aiming at the fortified walls anymore.
No, the Prussian artillery was moved closer, and they began firing directly into the city itself, heavily targeting the left bank. Over 23 nights, the Germans fired some 12,000 explosive shells into Paris.
12,000.
They were aiming their guns at the highest possible angles to achieve unprecedented range over the walls.
It was terrifying. Shells hit the Salpêtrière hospital. They hit the Théâtre de l'Odéon, which was being used as a hospital ward at the time.
Right.
The iconic dome of the Pantheon was a frequent target. When the French complained that hospitals were being targeted, Moltke coldly replied that he hoped to move his artillery closer soon so they could better identify the Red Cross flags.
That is so dark. But if we connect this to the bigger picture, Bismarck's goal was purely psychological warfare.
Okay.
He wanted to induce sheer terror, break the morale of the civilian population, and force an immediate surrender. But from a structural and psychological standpoint, the bombardment failed.
Which is wild. 12,000 explosive shells rained down on a densely populated city, yet the casualty reports show only about 400 people killed or wounded.
Yeah.
That math doesn't make sense unless there's something structurally unique about the city itself protecting them.
Well, Paris was its own shield. English observers at the time noted that the classic Parisian apartment buildings were constructed from massive, incredibly solid blocks of limestone.
Oh, interesting.
These heavy stone structures absorb the kinetic energy of the blasts. A heavy shell might displace a single massive stone or destroy a roof, but it rarely leveled the entire building.
And rather than causing mass panic, the bombardment seemed to harden the city's resolve. The terror turned into defiance.
Absolutely.
One local leader declared that they were the sons of Gauls for whom battles were holidays. Since the bombs couldn't break the buildings or the spirit of the people, the only thing that could force an end to this was the utter depletion of calories.
By late January, the food was entirely gone. Not just the meat, but the flour, the grain, everything. The death toll from disease and pure starvation became insurmountable.
On January 28, 1871, the government of national defense is forced to sign an armistice. The siege is finally over.
But the terms demanded by Bismarck are brutal.
Yeah. France has to pay a 200 million franc indemnity. The regular French troops have to surrender their weapons.
With the armistice signed, the blockades were finally lifted to allow humanitarian aid in, and the relief effort was a massive logistical undertaking.
The international response was huge.
Yeah.
Britain sent ships loaded with 10,000 tons of flour, tons of rice, biscuits, livestock.
Yeah.
The United States sent about $2 million worth of food. And we should definitely mention the unique role of the U.S. Minister to France, Elihu B. Washburn.
Oh, yes.
He was the only head of a major diplomatic mission who stayed in Paris for the entire siege. He acted as a neutral channel of communication and coordinated this massive humanitarian relief once the gates opened.
But food could not instantly cure the trauma. When the first British convoy arrived at Les Halles Market, the desperation was so high it actually sparked riots and pillaging.
Wow.
And beyond the physical trauma, there was a profound psychological humiliation inflicted on the French that would resonate for decades.
The ultimate insult. Just days before the armistice, on January 18th, Wilhelm II was officially proclaimed the German emperor.
Yeah.
And he didn't hold the ceremony in Berlin. He did it in the Hall of Mirrors at the Palace of Versailles, right outside Paris, inside the former home of French royalty.
Followed by a victory parade of 30,000 German troops marching directly through the streets of Paris on March 1st.
So what does this all mean for the listener today? The war is over, the city survived, but it feels like the historical ripple effects of these 4 months are completely massive.
Oh, the ripple effects define the next half-century of global politics. The siege didn't just end a war, it was the crucible that forged the modern German Empire.
Right.
It unified independent states like Bavaria and Saxony with Prussia into a single military and industrial superpower that would dominate the 20th century.
And the territory changes too.
Exactly. Bismarck secured the territory of Alsace-Lorraine for Germany, which planted the seeds of deep French resentment that would directly contribute to the outbreak of World War I.
And internally, the damage was just as severe. You have a Parisian working class that just spent 4 months freezing, watching their children die of typhoid, eating rats, and watching the wealthy hoard food.
Yeah.
I mean, only to be told their government surrendered anyway.
The Parisian working class and the National Guard were fundamentally radicalized by the profound inequality of the siege.
Yeah.
They were so resentful of their own government's capitulation that almost immediately after the Germans left, they rebelled.
Just months later.
Yeah, in March 1871, they formed the Paris Commune, a radical socialist government that took over the city, leading to a bloody internal civil war just months after the siege ended. The siege failed to break the physical walls of Paris, but it completely shattered its social fabric.
It's incredible to think about. 4 months that started with sheep grazing in a park and ended with the birth of a new global empire, the radicalization of a city, and a bloody revolution. Thank you for joining us on this deep dive into a period of history that saw humanity at its absolute most desperate and, strangely, its most inventive.
It is a profound historical moment, and it leaves us with something critical to consider. Think about the concept of a siege mentality.
Okay.
If 4 months of physical isolation, paranoia, and starvation could fundamentally rewire the political and social fabric of 19th century Paris, leading directly to an internal revolution, how does the trauma of modern isolation silently rewrite the rules of our own societies today?
That's a heavy thought.
Whether it's the physical lockdowns we've experienced or simply being trapped inside the invisible walls of algorithmic echo chambers, what kind of internal revolutions are we brewing right now?